Well, the proof of sum of n terms of geometric series. A geometric series has the first term a and the common difference r. Prove that the sum of first n terms of this series is given by Sn is equal to a into 1 minus Rn over 1 minus r. So geometric series. As we know that for the geometric series, there is a ratio. So for the proof, let Sn is equals to the sum of first n terms. A is the first term plus AR. If R is a ratio, multiply A by A to get the next terms and AR square. So in this way, you can keep on writing the terms and the last term is the nth term, which is AR n minus 1. You know this thing. And one term before is AR n minus 2. So these are n terms. First is a, second is a r power 1. The third term is a r square. The third term is with power 2, and if power is n minus 1, so this is the nth term. This is the nth term of geometric series. Now, to for the proof of Sn is equals to a into 1 minus r n over 1 minus r, I wrote the sum of n terms a plus ar plus ar square and so on. The last term is ar n minus 1 and the one term before is a r n minus 2. The next, what I can do next, uh, multiply both sides by r. So multiply both sides by r. So this is a special technique. So ar into Sn, you multiply ar square. So I'm multiplying left hand side by r and each and every term of the right hand side by r again. So this is ar cube and so on and so on. So if you multiply ar power n minus 1 by r, it is a r raised to the power n. And if you multiply the term before the last by r, it is a r n minus 1. So I multiplied both sides by r. So the last term in this way is a r n because simple. If you're multiplying a r power n minus 1 by r, so we have the same basis. It is a r power n minus 1 plus 1 cancel. So we have a r power n. So this is the last term. In the same way, the second last term you can write by multiplying. So simplification gives you a r n minus 1. So here is the second step. So after writing the second step, we want to reach this formula, which is sum of n terms. So next, I will subtract these two. I'll subtract these two, and yes, we know that for the subtraction, we change the sign of the second. So the second term. So this minus change plus to minus, change plus to minus, minus, and minus. So we'll be considering now these new signs because we want to subtract 1 minus 2, 2 equation number 1, and this is number 2. So actually 1 minus 2 or subtract 2 from 1. So yes, I'm changing the sign because of the subtraction. And next, what you can do, so you can observe here that we have AR in the first and minus. So we are now considering this sign. AR and minus AR cancel. AR square minus AR square cancel. So the same idea you can apply here. So ARn minus 1 and ARn minus 1 with negative sign cancel. So you can, so if as there are so many terms in between and all the terms will cancel, so you are left with only A here and AR and minus 1 here. So subtraction means uh, upper minus lower equation. So Sn minus Rsn is equal to A this term and minus r raised to the power n. So here is Sn common. If Sn is common, inside is 1 minus r is equals to A is common, 1 minus r raised to the power n. What I can do next, I can divide by 1 minus r. So A into 1 minus r n over 1 minus r. So this is the formula for the sum of, and this is wanted to prove. So this is the formula for the sum of first n terms of geometric series, and here is the proof. So yes. Next. So after this formula, the next proof is the formula for the sum to infinity. So this is, you can close this working here. Next is sum to infinity. Sum to infinity. Formula we know is that S infinity is A over 1 minus R. This is the formula for the sum to infinity. So A over 1 minus R. So what is the proof for this sum to infinity proof? As we know that sum of n terms is A into 1 minus R raised to the power n over 1 minus R. Sum to infinity means that if n is a very, very large number, n is the number of terms. So if there are thousands and thousands of terms, what will happen to this formula? So uh, if uh, uh, if n approaches to if n approaches to infinity, means if n is a big number, if n approaches to infinity, this n, if n approaches to infinity, then what will happen to this r to power n? If n approaches to infinity, you can say that r power n approaches to 0. So there was a condition for the sum to infinity formula, that this sum to infinity formula is applicable if r absolute value is less than 1, or I mean to say this, if r is a number between -1 and 1 and not equals to 0. So if this is the condition, so for the sum to infinity formula, r should be a number between -1 and 1, uh, excluding 0. You can write modulus of r is less than 1 excluding 0. So it means that r is a number less than 1. So just to explain this second thing, that why r power n approaches to infinity, I can give the counter example I can give. And this, like if there is a number, we say 0.5, if r is 0.5, this is the explanation to get why r power n approaches to 0. So if r is equal to 0.5, what will happen to 0.5 raised to the power infinity? Means 0.5 to power, say, you can use calculator. If it is 0.5 raised to the power, for example, 1000, so it is 0. Okay, or 0.5 raised to the power 100, for example. So 0.5 raised to the power 100 is 0.0000. So the answer is very, very close to 0. You can verify. Just example, 0.5 raised to the power 100, because 100 is a big number. So you will check that 0.5 to power 100 is approximately 0, but the answer is 0.0000 blah 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 blah, and there are 31 zeros. So and then 7 8. So 0.5 to power 100 approaches to infinity, and if you use calculator you can verify this thing, because 0.5 raised to the power 100 is actually 0.0000. There are 31 zeros and 30 zeros and then 7 8. So this is actually uh, approximately equals to 0, or you can say that this type of answer is approaching to 0. So here simply after giving this explanation, so simply in the proof you will write that r power n approaches to infinity, and if r is equals to say for example point 0.5 to power infinity approaches to 0, and infinity you can't write in the calculator, so zero point 0.5 to power 100, a very big number. So this is actually approaching to 0. The answer, as we increase the power of zero point 0.5, so the answer getting closer and closer to 0. So it means that this part for the formula, when n is very large, this part is approaching to 0. So finally, you can say that Sn approaching to, if you just ignore this part, it is A over 1 minus R. So I can write a formula that this happens when n is a large, when n approaches to infinity. So in the end, you can write a formula A over 1 minus R, and this is the proof for the sum to infinity of convergent geometric series.